I'm going to record the presentation to the extent possible. I don't want it to end up in a situation where people are not showing up in class. So please do show up for class. What we're going to do today is that I'm going to give you a general overview of the course, what we are going to be covering, what your expectation should be from the class. And this would be a good time where you let me know what your expectations are, especially if they don't match with this, and you can decide what we should do or whether you should drop the course. Any questions that you would have, and I'd sort of switch over to sort of a small mini lecture today where we talk about what big data is, at least as I see it. And we'll talk about assignment number 1 or assignment 0. It's not going to be graded unless you don't submit it. So I do want you to submit. You'll get negative marks if you do not submit it. It's not a very difficult task. I just want you to install Spark on your personal machines or whatever machines that you have. So that for subsequent assignments, you have a machine where you can test it. And so I'll go a little bit more into detail soon. That is the web page. It's also on Canvas, so we'll be using Canvas for most things. Occasionally there might be some material which is there on my web page, but I set it up in such a way that I'll try and push as much as possible onto Canvas, so you should be fine if you're using Canvas. Text and references. Mining of massive data sets. It's an online book. You can download a PDF. It's free. You can buy a printed version if you want to. This is the book that we would use for a reasonable portion of the material. There is other material which will be outside of the book, and I'll point you to material on my website. I'll upload it to Canvas or general resources. I'll make sure that you have other things that are available for anything that doesn't come out of this book. So again, like I said, for those of you who want, you can buy the book. For everybody else, an online version, PDFs, HTML, everything exists, including additional resources, which might not be covered in the class, but if you are interested in this general area, you can look into it, solve some additional problems, and use that for looking. We'll be using one of the CHPC clusters available to us, but you all need accounts on this. So there is a link. This link is also available via the course webpage. Remember, it's fall 2015, so make sure you fill out the right form for 2015. Fill out this form. All I need is your name, your UID, and your email address that you would like to use for this purpose, and we'll create accounts on this. The TA is Vairavan. Why don't you stand up so that everybody can see? Most of the time, you should be emailing him. If he can't resolve the issue, then email me or come see me. In either case, we'll both be having our office hours, which will be again updated on the web page. I'll try and put it up on Canvas as well. So again, most issues, email him, go see him during office hours. If not, come see me during my office hours or send me an email. Okay? My office hours are very simple. They're just preceding the class. So from 2 o'clock to 3 o'clock, every Tuesday and Thursday, I'll be in my office and you can come see me. Okay? If it's something more than one, sort of at the edges of what should be discussed in an office hour, please email me in advance and set up a separate appointment. This is going to be very important, which is class interaction. And I would strongly encourage that all of you have discussions and interactions both in class and via Canvas. So, in Canvas, most of you who are not fresh students and have used Canvas before, you can have discussions. So treat this as a grad class. I know there are a number of undergrads here, but use that to interact. So, ask questions, answer questions, help your peers in terms of being able to fix their issues in case you can. If not, the TA is there and I am there. There will be 10% credit for class interaction and online participation. A simple way to look at this is that this is a reasonable sized class. Please make sure that I know your name by the end of the semester. If I think of students who are sort of interacting in class, asking questions, answering questions, raising interesting points, again, both in class and online, then you will get those 10 extra credits, which might at least should be enough to bump your grade at least one level. I shouldn't have to mention it, but I will. These are the policies that all of you are supposed to adhere to, both from the College of Engineering as well as the School of Computing. For those of you who do not have time to read this, please, no cheating. That's the simple take home. Do it as you please. So, so the only way I would say that you're going to get, okay, I shouldn't say the only way, but close to the only way you're going to get a failing grade is if you are caught cheating. If you submit your assignments in time, if you do the project, and I'm going to get into what the specifics are, you should be easily getting a B, maybe even a B plus at least. So it shouldn't be very difficult for you to get a good grade, or at least an acceptable grade. So please do not cheat. It doesn't have to get to it. Do the best you can, and the rest you shouldn't have to worry as far as the grades are concerned. The rough outline in terms of how the course is structured, like I mentioned, assignment 0, which is due in 1 week, which is very simple. It's there online. If you go to my webpage, I'll also upload it to Canvas. It's not there on Canvas yet. There are links to install this on a Mac, Windows, and Linux. Beyond the links that are provided, I'm sure all of you are comfortable enough Googling for this and setting it up. There are some specific details. There's a specific version of Spark, which is what we're going to be using for this course, all the assignments that you should install, which is 1.2.1. And the main reason for this is, if you are more adventurous, you can install the more recent version. The main reason I'm stressing on 1.2.1 is that is what is installed and used by the cluster that we're going to be using. So matching the development environments is going to just make your life easier, and maybe our life easier as well. So just stick to that, install it, have it set up. Assignments 1, 2, these are going to be relatively simple, I would say. Shouldn't take most of you who have reasonable programming experience maybe more than 15 minutes to half an hour to solve. These are intended to get you started. These are small problems in Spark. I'm just going to give you 1 week, but the main intention is for you to get familiar with the language, familiar with the environment, and familiar in running these things, sort of developing on your laptops, on your own machines, and submitting jobs on the cluster. So this is sort of, treat this as teething problems. Like I said, assignment 0 is not going to be graded unless you don't submit. I just want a confirmation from you all, or the TA rather, needs a confirmation from you all that you have installed it and that you're able to run the standard examples that comes with the package. So just make sure you can submit some of these so that assignments 1 and 2 go smoothly. They're very simple problems. Assignments 3 and 4 are going to be a little bit more involved. These are I'm going to be providing you sort of smaller size data sets so that you can run and test these on your laptops, but for the actual assignment you will have to submit it or run it on a larger problem on the cluster. For those of you who have beefier laptops, you might be able to run the larger problems on your machines as well, but you should try and run it on the larger machine. You're going to get 2 weeks each, and there are going to be no extensions. I want you to be particularly careful about this. We are going to be running these large problems, not the ones you run on your laptop. We're going to be running it on the cluster. It's a shared resources, and you can see there are plenty of students who are all going to be competing for these resources. So do not treat this assignment as an assignment that you want to start working the weekend before the submission is due and you think you're going to get done with it. You should start it well in advance. If you have 2 weeks, I would almost say that try to finish at least the basic programming done in the first week so that you have the second week to submit your jobs and get it through. One of the biggest challenges that you will face in any of these large big data type problems is in making it run it at scale. Not in writing the basic code, but getting it to run at scale and making sure that you can use the resources effectively and efficiently. So please do not wait until the last minute. I know that the machine and the cluster are going to be It's going to be difficult for you to get your jobs run through. It's going to be difficult to guarantee that your results come back. The system might crash. Short of the machine being offline, say for the entire 1 week out of this 2 weeks that you get assigned, that is not going to be an excuse I want to hear. Okay? So if there are significant problems with the machine, I will accommodate it, but I want you to do enough of it. And to an extent possible, you should sort of start experimenting on these baby problems itself, where you're not required to run it on the large machine, but you should play around, make sure that you're comfortable running it. And if there are any problems, bring it to the TAs or my attention. Is this clear generally? So make sure you're there. The biggest chunk of your credit is going to be based off the final project. To a large extent, this is what you're going to be working on in the second half of the course. We're going to be having lectures, but a big portion of your work is going to depend on the final project. I want you all to submit proposals before the fall break. So you should start thinking there's not a lot of time. While you're working on these assignments gearing up, you need to get ready for your proposal, right? So you need to submit a short 2-page summary, and I'll put more details on exactly what I expect from you on this and get it approved. So I will read through your proposals over the fall break, and once you're back from the fall break, I'll give you feedback. And it doesn't hurt for you to come and talk to me either during office hours or otherwise via email on what you think might make a good project. Okay? I want it to be formalized for all of you by the end of the fall break. Is that fine? We will have some sort of sanity checks in between, so you can sort of potentially treat those as other assignments where I want you to submit a report of where you've reached, what you've achieved, and what else needs to be done. So do not think that the second half is going to be, on a sort of a free, without any milestone form. You can have 2 to 3 students per group. And I want you to warn here again, I'm fine with having 2 or 3 students per group, but please make sure that you choose your partners wisely. I don't want anybody to come to me and say that my partners are not working. So especially by the time you get to your final projects, be comfortable with the people that you have chosen to work with. Yes?
So this is 2 students per group for all assignments?
Yes. So again, I want to also warn you that in most of these cases, I'll try and give you a large project, especially a single large problem. For assignment 1, 2, which are basically toy problems, even though I'm fine with you all submitting, this is for a very small portion of your grade anyway, I want you all to do it independently as well. Take this as, I have to balance out between making sure that each of you actually gains as much out of the course between how much me or the TA has to grade. So I don't want it to get to a stage where I'm policing each and every one of them. For your own sakes, to the extent possible, I would say that use the group work, and this is going to be much more important for assignment 3, 4, as well as your final project, where you want to push the limits of beyond even what I define as the project, especially when you work in a team. So there's a certain amount that you are going to be able to achieve individually, and I want you to be able to push it. And I'll give you sort of stretch tasks in terms of things that you should try to achieve. And that's how I would look at it. For the project, choose well. And I would almost, to an extent, recommend that in the earlier assignments that we have, you might want to experiment with different group members to see that, to make sure that you have a good working dynamic. So, like I said, the final project is going to be important, so you want to choose your team members wisely. I'm fine, especially for assignments 1 and 2, if you do want to do it individually. That is okay for me. It's okay for the other ones as well, but just at least talk to either me or the TA. There is going to be a midterm after the fall break. It won't be probably I'll try not to have it the first class after fall break, but possibly in the first or second week after fall break, we'll have a midterm exam so that we can test some of these concepts. So you're submitting your proposals before the fall break, and you're having an exam after the fall break. Is that fine? Any questions? Okay. Things that you should know. There are no formal prerequisites for the course, but having sort of a good programming skills in any language is going to help. Spark offers interfaces in Python, Scala, and Java, and I'm fine with you using any of these. I am personally going to be using Python during the lectures whenever I want to show you code examples or any of these cases. I want to show that in Python, but if you are comfortable with any of the other interfaces, as far as Spark is concerned, it's just exposing an API and everything is happening behind the back. If you want, and if you're comfortable with functional programming, Scala might be a better choice, and I can help you out with this, but like I said, for ease of presentation, Python is going to be what I use in my class. Okay? And again, if you want to do something funkier than this, you can make a case. It's probably easiest to say everybody does it in Spark, but I'm open to it if you want to make a strong case. Again, be prepared to learn new programming tools, languages, and techniques. The goal of this course is not to teach you Spark or Scala or Python or any of these things. Programming languages and the platforms that you use are tools. You want to be good computer scientists, that the fundamentals are strong, and so 2 years down the line, if a new language comes along which is better suited for it, you are able to adapt to it and use it. We are using Spark here as one particular tool that makes it easy for us to streamline. Focus on the techniques beyond just programming, and that's what I want you to learn. Beyond that, a knowledge of linear algebra is going to be useful. A lot of the algorithms that we are going to be using as a background, that's not the core content out here, but you still, I can't design large scalable algorithms in the absence of data analytics algorithms. A lot of them would require some basic math, linear algebra, statistics, so most of you should have this background. Of course, you need to have done an undergrad algorithms course at least, so you know sequential algorithms. You're going to be doing things at a large scale and in parallel, but you need to understand sequential algorithms and how we do complexity analysis. And this is sort of going to be one of the key factors, is that you need to be able to look at a problem and figure out what is the optimal way to run this. Do we need to run this on a single machine? Do I need to run it on a very large cluster? And you need to be able to analyze it. What is the most efficient way to do it? How should I break up my problem so that I can run it in an efficient fashion? And so for some of that, we'll be doing theoretical analysis of the algorithms themselves. There is a rough outline of the kind of topics we're going to be covering. So early on, we're going to lay the groundwork, both Hadoop and Spark, MapReduce. We'll go through parallel algorithms so that we can analyze these. We're going to look at some sort of what would be the equivalent of fundamental algorithms and data structures. So we're going to be looking at sorting and searching in parallel. We're going to look at some randomized algorithms. And then we'll sort of switch gear, hopefully around the fall break. We're going to look at popular data analytics algorithms, and then we'll look at how do we actually implement this in something like Spark or any of these large data analytics frameworks. So we're going to sort of look at these cases, and hopefully we have time to hit some of these large-scale machine learning problems as well. So for those of you who might be taking machine learning, I've kept it right at the end so that we can play with that. Any questions on this? So I sort of covered this, but here it is for those cases. The focus is going to be on understanding big data algorithms and ensuring scalability for large-scale problems. This is what I want you to be able to take home. That tomorrow, either as part of your research or you're working for one of the tech companies out there and you need to solve a problem, you want to be able to take it and make the right choices for how you're going to implement it, how you're going to execute it. And that's what it is going to be. We'll be using Spark and Python, but the skills acquired should be transferable to any other platform or framework available out there. So do not get entangled or caught up with what the framework offers you. I want you to think beyond that. Think of the fundamental techniques that you're learning and how you will apply it. And for those of you who might be using other frameworks, you want to be constantly thinking about that as well. That here are the core issues, this is how I would do it in Spark, but how does that translate to other frameworks? Okay? I'll try and give you examples whenever I can think of one. I also mentioned this that I will show you code examples. Do not take this as a course where you're going to learn how to program in Java, Python, or Scala. That's not the focus of the course. Programming assignments will be frequent and hard. I've told you what the structure is, and I also told you that the cluster is going to be unreliable, so you should not wait until the last evening to test your code. So please make sure that when you're writing code, this is especially important for assignment 3 and 4, that at whatever stage you've finished, say, part of your assignment, do test it on the large data set. Do be aware of what it entails and where things might fail. So you need to sort of do this in an iterative fashion and not wait that, this code runs on this baby problem on my laptop, so it's guaranteed to run on the large cluster as well. So make sure that you do this in a frequent fashion so that you don't email me in panic, one day before the deadline saying that I'm not able to run my job on the cluster.
I have a question.
Yes.
So so it sounds like, okay, assignments 3 and 4 are going to be quite a bit more heavy on the workload and
yes.
on the compute cluster.
Yes.
And so, I mean, it depends on resources available, but on general, is it going to take like 24 hours?
No, it should not. So I'll give you problems that are large, but should not require a very large window.
Okay.
So I'll try and give you problems which are going to be large, but will once running should not take you more than, say, again, we'll have to test it on the actual machine by 15 minutes to half an hour, say, order of that. So you should be able to, but it's not going to happen if everybody submits. So there are two separate aspects, right? Is the time to which you get to the head of the queue, and then it executes. So you don't want, if everybody is fighting for the same resources, then there's going to be a problem in getting the kind of guarantees of performance that you're expecting. So what I want you to do is that, and depending on how it goes, I might either decide to give you slots in which you want to run it, or I would ideally assume that all of you do not wait until the last day, in which case, statistically it should be fine for you to finish your jobs. So think of it that way. The other option would be that, do you want to do this? Do you want to submit all their jobs in the end once they've submitted the code in a single script?
I think it would be better if they submit.
Okay.
After that.
Okay. We'll see. If assignment 3 has a lot of problems, we might revisit how, but I would ideally prefer it if you are responsible. To some extent, I want you to realize and to understand that the moment you're running a job, it's not like you running on a dedicated workstation. So the moment you're running it, this is going to be your life. This is your job, right? So you have to get used to it, and you have to plan yourself according to this.
Yeah.
So test often, test when you can. Make sure that you're not restricting yourself to testing it only on your laptop. So if you have say you finished stage 1, let me make sure stage 1 works on the large machine as well. So that's how I would look at it. I want to sort of get your opinion on this. I mentioned that the final project is going to be a significant portion of your grade. Now, a lot of you are probably master students, a lot of you are probably not very interested in research. Do you want me to give you a default project? I still want it to be open for those of you who are looking to push it forward, but how many of you would prefer if I gave a default project for everybody who is not going to pick their own projects? Who's in favor?
As an option.
As an option. Don't think it's going to be less work. I'll probably make it, yes. So, yes, you're not going, you might not have to submit a proposal, but I'll make sure that you do something else instead. So, I do not want it to be a way for you to sort of, skip out of getting work done. This is only for people who think they are not going to be able to do something interesting. The way I would look at it is that you should try and find a problem that excites you and work towards that. It's a significant portion of your grade, and you should be excited about some particular problem that you want to solve. And it could be from the topics that we're going to cover in class, it can be from beyond that, and you can come and talk to me. Like I said, it's going to be on the second half of the semester, so there'll be a lot of time. You can discuss it with me, and I can help you with that as well. So, again, don't look at it as something that's going to be easier for you to do. It's possible that if you choose an interesting enough project, the amount of work that you do would be less than what you're going to do for the default project. So this is just for people who are not interested in exploring things. I can give you a default project. Do you still want a default project? Okay, I will give you a default project, but again, I just want to warn you that the default project is, don't treat it as an easy alternative. I'll make it reasonably challenging. Okay? And I'm hoping that by the time you guys get done with assignment 3 and 4, that should give you an idea of what your expectations from the final project should be. So any questions before we move on? Just with the logistics, the course structure, anything else related to that? Yes?
So all the 4 assignments are in the first half of the
Yes.
one week?
Yes. Again, if you are trying to juggle courses or do anything, do not think that the second half is going to be. So think of the second half being part of your project in, say, 3 parts. So there is, let's think of, for your planning purposes, you can think there is assignment 5 and assignment 6, which are part 1 and part 2 of your final project. So there will be checkpoints, because I don't want, again, you all to show up on 1 week before the end of semester and say that I haven't done anything for my project. So there will be checkpoints where you are submitting things, presenting work. And like I said, the proposal that you submit before the start of fall break is the start of your project. So you should actually think of the project as something that spans the whole semester. So over the next few lectures, as you get familiar with Spark, as you get familiar running some simple examples, which are going to be assignments 1 and 2, you should already sort of start thinking about where you would like your final project to go, and start discussing with me, with a TA, with your friends, anybody else who's interested, what might be an interesting problem to work on. And then, as you're getting closer to the fall break, prepare your final proposal, send it to me, and I'll give you feedback by the end of the fall break. Yes.
So with any, as you know, machine learning, data mining, anything that way, there's always theory behind it.
Yes.
So how much of this course will be dedicated towards the theory and the practical application?
So I will cover the theory and the methods to the extent that I needed to explain how to take these and scale them. So the set of algorithms that I've chosen are somewhat representative of very different computational ways of analyzing data. So don't take this as a replacement for a deep theoretical or application-driven data mining or data analytics course, but there will be an overlap. The overlap in the sense that it's easier for me to pick one of those as an example algorithm and then talk about if your algorithm structure, if the specific analytics that you are interested in performing matches this class of problems, then this is how you go about doing this. So think of this as a course that will complement a traditional data mining course, although there will be a reasonable amount of overlap. But I want the focus to be on how you take what you would learn there and maybe implement it in R or MATLAB or something. And if you want to do this on a large scale, then what are the considerations that you have? How do we analyze whether indeed you should be running this on a single machine and using R, or whether you should be using Spark already for it. So that's sort of how I would like to be. And like I said, it's difficult for me to teach you that in isolation, so I will cover the basics of the algorithm itself. I might just spend a little bit more time talking about the parallelization aspect and analysis from a parallelization perspective, as opposed to the exact bounds of your error or anything else like that.
Okay.
Yeah? Yes?
So for
Yes, you will have a presentation and you will submit a report. And the presentation, because we're not having a final exam towards, let's say, the last week of classes, and you're maybe, because it's a big class, I might have to stretch on into the exam week as well. I'll schedule presentations for all of you, and you can present your work. And I think that's also important because you're all going to be doing, as you have promised, very interesting projects that you're going to pick. And hopefully there's only one or two groups who do the default project. So I want you to share your experiences on that as well, because there's a very vast area. There's a lot of specifics in each of the specific different kinds of problems that you might pick. So it's important to share it with everybody else. So that, again, when you work towards your project and you talk about your work in the presentation, talk about the challenges that you had and what you had to do specifically to overcome it, so that even people who haven't worked on it at least get something out of it. So I'm going to sort of give a very quick overview of some of the things, and I'm going to slowly start getting into what is big data and what it means to process it on these large frameworks that have come about. So what is big data? So let's have some answers. What do you think big data is? Yes.
It's taking to get meaningful information out of a big chunk of data.
Okay. What isn't big data?
Sorry?
What isn't big data then? You're always trying to get something meaningful from a chunk of data, right? Or for the most part. Yes.
I just think it deals very much with the size of the data that you're dealing with. So you're going into terabytes, into petabytes, and processing that instead of a file or two files or whatever in that manner.
Okay. So this is Dilbert's definition, or almost. So, and I want you to take it. So, to a large extent, when you hear big data, there's a lot of jargon in it. There's sort of industry talk, trying to hype up something which has existed. There's always been a big data problem in some sense. And to a large extent, the amount of data that we have right now, although it has grown, the vast majority of problems that might be classified as big data problems are not really that big. And they're not. So one of the key things is for you to look beyond that. So it's fine when you want to talk about it and you want to use the jargon, you want to sell whatever you've done, it's fine. But at least when you're thinking about solving the specific problem, you need to be honest about it and look beyond the jargon, right? At the fundamental level, you have some data and you want to process it, you need to extract something out of it, and that's perfectly fine. Yes.
I think maybe another way of putting it would be that it's when what we're doing is a lot of parallel processing. That is, all that data, we're not putting it directly, the entire set in the memory or analyzing the whole set. We're only analyzing a part of the set.
That is partly true, and as we will look through this, you will see. So what you're saying is where parts of your data can be analyzed or evaluated in isolation of the rest. And so this would be what I would loosely call as embarrassingly parallel. So there are very few data dependencies. And you would sort of see that amongst the sort of the poster child of, say, the start of your big data terminology is when you look at PageRank, where it's actually not that isolated. So you have to actually process it. There are dependencies in data which need to be processed. And we'll sort of go a little bit into it. And again, I'm not putting this up in a sort of a dismissive fashion. I just want you to focus on what it is and not get carried away by the jargon. So focus on what the problem is. And be very, very aware of one thing, because there are a lot of papers, and I can point you to some sort of additional reading where, recently some researchers decided that, let's look at the top papers from the top conferences where this kind of work gets published. And they were trying to see the kind of performance that people are getting. and whether it really requires it. And this is in almost all cases, for exactly the same data sets, they were able to process it faster on their own laptops than what are being reported for, say, running on hundreds or thousands of machines in parallel. So you need to be able to analyze your problem, be smart about it. Just don't immediately say that this looks like a big problem, let me just throw it at this large cluster that I have available. So you need to be able to do it. And the typical case is that if you are, let's say, doing something as trivial as a word count, right? Or maybe you want to compute page ranks, or you want to basically see the importance of certain nodes in a graph, maybe a social network graph. You want to figure out who is the best one to start a viral marketing for me. Depending on the size of the problem that you have, the specific algorithm that you need to run, is this something that I should be running on my laptop, on a beefed up workstation, with, say, a few terabytes of RAM? And you can get those kind of machines now. Or should I really be running it on a cluster of 10 nodes or a cluster of 1,000 nodes, right? These are the kind of questions that you need to, hopefully you will be able to answer these questions at the end of this course. And that's what is important, right? Now, take this with a pinch of salt, because a lot of times you're going to have to make do with whatever resources you have available. But if you do have the choice, you want to be able to figure it out and do it in an efficient fashion. Not just blindly code up the first thing that comes in your mind and throw it at the cluster. And that's not going to work for your assignments either. So make sure that you focus on that. So, a nice chart by IBM, and some folks from IBM also coined what you might hear quite frequently as the 4 V's of big data. I think sometimes people come up with a 5th and a 6th version as well. But loosely, let's sort of talk in terms of it. For most people, the first V, or the volume, is what is going to be important. As I mentioned earlier, I'll put the slides online and I'll put the videos online in most cases as well. But yes. So if you want to look at this particular poster in detail, effectively the first part is the volume, or the size of your data, right? We have tons of data. A lot of you mentioned, the gazillion tweets being sent out, all your messages on Facebook, all your web searches, all the web posts, people's blogging, everything. There's tons of data being generated. But significantly, where does it really matter for us? Where is the maximum amount of data being generated? That would be interesting. Again, where is, sorry? Yeah, it is on the internet, yes. I mean, specifically, what kind of data is really going to, so I think you might even probably find it. So what is most of today's internet traffic?
Social activity.
No, it's not. It's not. I mean, at least not directly.
Searching e-commerce.
No, it's Netflix and YouTube. It's video, right? Just in bytes. Always think it's not. I'm not bothered about billions of tweets. If you're thinking about processing, the quantity of data, right? There are other issues when you think about social networks and what is happening. But in terms of raw bytes that are being sent over the internet, that is what is dominating. So you'll find a lot of people, that's why you need to be careful and not being sidetracked by, say, companies like Twitter or Facebook, because the ones where real sort of engineering is being done in terms of making sure that you can do this. And again, when you think in terms of, how does YouTube sort of figure out what sort of ads to put in place when you're watching a video? That's really talking in terms of a lot of data being processed. You're watching it on your tablet, you're watching it on your laptop, somebody's watching it on the phone. There is all this processing that needs to be done to route that content to you. That's where the volume is, right? Everything else is there, but when you look at the other factor, you have velocity. Yes?
When you say the volume of data, for example, the video data is huge.
Yes.
But most of the processing of the video data is done based on the metadata, which is again text.
Yes, you're absolutely right. So that comes to the second part, which I said that you want to look at the kind of data you have and the processing that you're doing, right? That's why I gave the example of sort of something like transcoding video, which is being done, which has to be done on the actual video data itself. But when you think in terms of all the numbers that you hear about, traffic on the internet, they are heavily skewed because of the amount of video and secondly, audio data. These are your large files on your machine. This is what takes up bandwidth when people are exchanging. When it comes to analytics, yes, when you look in terms of volume, you'll talk in terms of bytes. You can always talk in terms of, say, if you're looking at tweets, I'm looking at number of tweets, and then that becomes significant compared to if you're looking at the number of videos, or if you're looking at, say, the number of documents that you might have. So there is a trade-off, and the processing that you're doing, that's why when we look at complexities, we'll have to look at what is it that you're processing on. Whether the N in your complexity is going to depend on the actual raw data or metadata that you might have, and again, where the counter is. So I'm not saying this, and again, this is the first lecture, so take most of what I say with a pinch of salt. There are going to be specific cases where processing any of those is going to be challenging. And when we sort of, towards the second half, when we look at things like social networks, where it will become important on why those things are challenging. It's not the actual amount of raw data in many of them where it is challenging, and actually analyzing those kind of complex graphs, which have very skewed data dependencies, is where the challenges are. Right? You can actually represent a lot of those social network graphs even on a reasonable sized single machine, but the computational complexity of processing that information can be very expensive. So that's a sort of a completely different kind of a beast that we have to deal with. When we talk about volume and you're typically looking at bytes of data, that's where the dominant part is.
So the problem here when we look at that volume of data is specifically the storage, not the analytics part of it.
Well, yes and no. So it depends on how it is stored and how you're going to be fetching it. So you will either have to design special, because, so think in terms of gazillions of videos being uploaded to YouTube, right? You then have this issue of extracting this. So you are fetching a lot of information and then figuring out whether something, whatever metadata needs to be extracted. So that it usually happens in stages, but you still have to process it. And actually a lot of the current work on video advertising does actually analyze the video frames themselves, either to say that there is a cutesy, there is an accident happening here and we should have an advertisement for an insurance policy or something like that. A lot of kittens out there like advertise, pet food alongside that. But you have to, that's the stage at which we are, wherein people hype up a lot of these things early on, but eventually we are still somewhat far off from analyzing all of this data. So whenever you see, so one classic example is that a few years ago, most of what Google did in its image search was based on auxiliary content around the image. So whatever text is surrounding it gave you cues to what the image is. But slowly, because they are able to process this in a more efficient fashion, and computational powers have increased, you can actually do specific image searches as well, wherein the content is being analyzed, the actual image data is being analyzed. And so that trade-off always exists. And I don't want you to limit yourselves to sort of what is technologically possible today. You want to be able to look at scaling that out into the future, where you will have algorithms where you can process vast amounts of videos or images or any other, the next generation of large data types that we'll end up with. So there are sort of two factors to consider here, just the raw size of the data and the quantity in which you have it, right? The number of video files that you might have or the number of documents that you might have. So there is always this trade-off between them. So is that okay? Yeah. So the other factor that you want to consider is velocity. And it's again, this is more of jargon where they wanted 4 V's, but fundamentally what you're looking at is the rate at which data is changing or how dynamic the data is. So when you have data which changes very fast and you need to process that, the kind of algorithm that you would need. So a good example would be, say, for example, if you're analyzing stock data, right? It's changing very fast and you want to react to it. Maybe there are tweets on an earthquake that takes place and people are tweeting and you want to react to that in a fast enough fashion. So then that requires a separate kind of processing and the kind of algorithms that would analyze the data, and computationally how you would deal with this when you have locally very fastly moving data. Variety is another headache that a lot of people have. Typically when you deal with online information, you have a lot of data available, but sort of gathering it all together and processing it becomes difficult, mainly because of not having a common standard. Data comes in different formats, and you have to effectively, one of our new faculty members who's joining, actually some of his research has been on this, where you will have a common way to plug into different sources of data and query it and process it. And because it might seem like a non-issue almost, but it becomes a big problem because you expect that all this data is available, but you can't really process it because it's coming from very different sources. The last part, of course, is veracity, where it's better to maybe look at it in terms of the second line out here, which is uncertainty. Now, uncertainty comes from the quality of the data. Some of it is very simple, right? In terms of uncertainty in, so maybe temperature readings, and there is a certain amount of noise that is there. But more importantly, at least when you look at sort of online content, there is fake news articles that are written by people. There's blogs. So if you start searching for it, and you might have read about articles where in Google, there were paid search results which were popping up when you searched for things like evolution. So you have this notion, because it's a free-for-all, people who are shouting the loudest have a chance to be heard. In this case, the people who would, and we'll sort of look at this as well when we are looking at algorithms like PageRank. How do you make sure that your web page is the first one that ends up when you search for some pages, for some information? So when you want to process it and you want to get something meaningful out of this vast amount of data that is out there, you have to factor in how you're going to deal with, oops, that's not right. With one of you mentioned this right in the beginning, is that data is sort of at the center of the digital world, and the key challenges in making use of it. So how the amount of data that you have, the rate at which it's changing, the uncertainty that we have in this data. But what is big really depends on the application domain. So what is big in terms of when you're analyzing tweets or if you're analyzing news feeds is very different from what might be big when you consider, say, bioinformatics or genomics data, image data or video data, right? So the application domain is to a large extent going to dictate what you define as big. And each of them have their own challenges. So if you come from an application domain where most people are processing things on their laptops or in JavaScript, then there is an issue, right? Their definitions of big is going to be very different from people who are, say, processing tons of videos on a daily basis. So keep that in mind. And so when you see the word big, especially in context of big data being used, always wait in with what the application domain is. Of course, that's one of the reasons why we can look in terms of what kind of data we're talking about. You have web data and web data accesses. So what is it that you are contributing towards Google's data pile when you do your searches? You have maybe, a few hundred words on a daily basis, which is not a ton of data out there, but spread across billions of users. That's sizable, but still not something that significant, a few gigabytes of data on a daily basis, right? And especially if you start sort of compacting it, because you're probably searching for the same kind of things on a daily basis, over a period of time, Google doesn't really need that much of data to build its repository of searches, right? What are keywords that people search for at what frequency? So you need to sort of be aware of it. It might look like a large problem, but it's not. Emails, chats, tweets, still predominantly text, not a huge amount of data, at least in terms of storage or being able to analyze it. If you start looking at telephone data, mobile, so NSA might be tapping in and recording your conversations. This gets into the sound domain unless you have somebody who's transcribing it and keeping it as text. So this is significantly bigger. You have public database, gene banks, census records going back years. People are interested in these things. Again, if it's not digital, like old scanned versions of census records, that adds a complexity in terms of what the size is, even though the technical content, what you were calling as metadata in that sense, some sense, is much smaller. So if it was actually extracted out of it, the real content is much smaller than, say, a high-resolution scan of an old document. So this sort of adds an extra layer that you have to sort of consider. There are also a lot of private databases where security becomes important. You could have sensor data, camera surveillance. Many of you are probably wearing sensors, which track your movements. Your phones do that. So there's a lot of this kind of information which is there. Data is also valuable. I'm sure all of you know this, that Google and Facebook make tons of money by mining your data, for the most part by offering you to sell things to you, whether it is advertisements or directing you're hungry and which pizza place would you rather go to. So that's where the money is being made. Of course, financial firms do this. Medical records can be processed in terms of analyzing it to figure out whether treatments can be better or possibly cheaper. You have data that is gathered from traffic cameras where you can do traffic analysis. There's a security application where face detection in airports, for example, trying to spot criminals or terrorists. One aspect which I did cover last time, but I'm not actually going to spend much time this time, is collection of big data. I did mention that there's a ton of data out there. It's all in different formats and sources. And it's still difficult to get your hands on it. Sometimes because you don't have direct access, you can't have access to what Google owns or what Facebook owns. You have sort of samplings of it. Even as far as Twitter is concerned, you can sort of get samplings of tweets, and you have some ways of filtering it out. But if you want access to the actual data, you either have to pay for it or be the company itself who's acquiring it. There's also a lot of redundancy in the data. So, let's say that you're interested in gathering information, looking at web pages, they get replicated, tweets get retweeted. So then you have this whole issue of how do you actually make sure that you have a unique amount of information that you're interested in without the noise or the redundancy. So this is something that when many of you are considering about your projects, you might want to consider whether data is readily available or it's something that you would like to incorporate as part of your project. Where, how are you getting information, gathering the actual data before you can process it. This is sort of a quick overview of where we have moved in. So processing and analysis of big data has sort of become more challenging, mainly from the perspective that large data sets do not fit in memory. I think one of you mentioned this. So the usual approaches, there are two ways to circumvent this when you have a problem or a data set that doesn't fit with memory. What would be the two ways of going about doing this? Or maybe three ways, let's see. What's the easiest solution? Yes, exactly. So that would be the easiest. Let's get more memory. And at some point, there's a limit to how much you can add at a given time. Maybe you wait a few years, you'll be able to increase the memory. What is another option?
Use disk to store data instead.
Okay, disks to store. And what were you saying?
As it uses the existing replica of the data somewhere instead of.
How are you going to solve the problem? So maybe you're all meaning the same thing, so I'll sort of rephrase it. Effectively, this would be what usually is called as an out-of-core algorithm. So you read a chunk of data, process it, write back. So use your disk storage as an added layer of memory where you are taking a performance hit because I have to do a significant amount of I/O every time I need to sort of read and write back chunks of data. And for a very long time, this is how larger problems were solved. You read in a piece of data, processed it, wrote back, sometimes in a redundant fashion, and it took a lot of extra time. So what you could say, if So the scalability would never be linear in this case, because you would read in a little bit, you would write back, but then anytime I need more than the amount of data that would fit into memory, I'll have to develop special algorithms which will be able to process this. What is the third way?
Streaming. So.
But streaming sort of.
I mean, because
Is
you
it
would
class?
keep a representation of that data, and
Yes.
everything else would come through and modify it.
Yes.
Is that okay?
There is a difference between the two things, but I'm sort of loosely clubbing them together in the sense that you're using your. So there is a certain amount of algorithmic sophistication in being able to design a streaming version of an algorithm.
Okay.
But at a fundamental level, they're both using disk space as the section. The third one, which is surprising, I would have expected sooner an answer in that direction, is to use basically a cluster or distributed memory. So you have multiple machines, each have their own memory. So the earliest solutions were all based off this, where you start replicating machines, have a way for them to communicate with each other. So if the maximum amount of memory I could have on a single machine was limited to 16 gigabytes maybe, then I string together 10 of these and I have a machine which is at least looks like it has 160 gigabytes, right? Now, obviously, in each of these cases, there is a complication, not the first one, but the moment you have to do out of core or distributed memory processing, you have to design new algorithms. You need a way to communicate, exchange data, or process your data in this fashion. The earliest versions, which go back to 1991, was the message passing interface. We're not going to be covering this. If you're more interested in this, this is still very widely used. Take the course that I offer in spring. It's a low level or a much lower level than what we're going to be using, interface or an API for C Fortran communication. What it does is that it's very, very powerful. It handles it at a much lower case, gives you a lot of flexibility and gives you a lot of performance. The one reason why it's sort of become less popular for large-scale data processing is that it's not fault tolerant. And you need to sort of understand this, because a lot of people will not tell you the story. So traditionally, MPI has been used on what would be known as high-performance computers. And these are supercomputers, these are very expensive machines, usually of a very high quality, and as a result, fault tolerance is sort of tossed on to the hardware and the lower operating system layers, as opposed to being on the application level, right? What happens is that with the early .NET companies started coming out, when you started having all these internet companies, Google typically, they didn't want to spend money on these kind of machines. So they wanted to pick up a cheap workstation, plug a bunch of them together, and have it up and running. This is no longer the case. Some companies still do it. I think Google probably still does it to a certain extent. Where you start having companies realizing that that's not a cost-effective model. It's a good model for a startup if you don't want to spend a lot of money and you want to show things up and running at scale. So fault tolerance became very, very popular, almost at the cost of performance. So MapReduce, which was introduced by Google in 2004, originated from web data processing. So some of the earliest tasks that Google had were very simple, sort of like literally scraping metadata off large, web pages, which are all distributed in a sense, and it really didn't matter. So if a node goes down, it doesn't matter. Another node is going to repeat that task, and there's a lot of redundancy in the system, and you will do it. The goal was on ease of programming, typically ease of programming for people who are not trained in distributed systems. So you're used to a certain kind of workflow, a certain kind of programming style, and you don't have to change that much, and you still are getting your job done. This is still largely true for a lot of the companies, but this is changing, and we'll look at it when you are implementing some of your algorithms, because not all your algorithms are easy to map onto MapReduce. There is also a sort of an added thing that you should be aware of when you read things. Google has dual standards. They if you look at what they do in-house versus what they advertise to the rest of the world, there is a big discrepancy. So Google does things very efficiently in-house and sort of kind of puts everybody else on the wrong track. This MapReduce is a classic example of this, where Google have their own internal C++ implementation of MapReduce, which is very efficient, and the rest of the world uses Hadoop, which is not very efficient. And one of the key things out here is that there are limited semantics, because there's a certain class of problems that are easily mapped onto MapReduce, but it's not going to work for all examples. PageRank, which, like I said, is one of the early cases, is a good example of something which doesn't really work. So over the years, what has happened is that different companies have all built their own solutions, almost duct tape on top of MapReduce and Hadoop. One of the things which has become very dominant and very popular of late is Spark, which came out of Berkeley and is now part of Apache and everything else built on top of that, which kind of plays a game in between what MPI does and MapReduce does. And it works on top of a Hadoop layer as well, beyond several others, where it allows you to cache information, which means that you have a choice of what information, to a certain extent, what information stays in memory and what information is sort of synchronized back into disk, and what is the level of redundancy that you have. We'll look a little bit into this in detail later, but fundamentally, this is sort of has been the evolution, and because Spark is sort of the most commonly used platform for data analytics, we're going to be using that for our lecture, for this class. I'm going to skip these two things, and since we are running out of time, I will introduce this because this is what I want you to focus on. And we'll continue from this again next class, but since we have about 10 minutes, I want to go through this. What I want you to sort of start thinking about as we go about this class is parallel thinking, which is that you want to be able to take a problem and break it down into pieces so that you can process it in parallel. So let's sort of go back to this expression by Seymour Cray, who's universally regarded as the father of parallel and supercomputing. So he asked a question, which is really weird because he effectively went ahead and did something along these lines, that if you were plowing a field, what would you rather use? 2 strong oxen or 1,024 chickens? So what would you use? So this is coming from somebody who's actually advocating the exact opposite a few years from when he made this code. But let's sort of look at where we are. So if you consider a single ox, right? For a very long time, this is where we were. You know, let's go and get the strongest ox that I can buy, and let's use that to plow our field. I'll get done faster. So this is what your single core performance can be equated to. So we were in a generation where, you know, every year you would get a faster process. I'm sure you are not that young, so I'm sure you've lived through this. You know, 1 gigahertz, 2 gigahertz, 3 gigahertz, you know, 3.4, and then you stop, right? You're not getting faster processors anymore. So basically we are at a level where you can't really get a stronger ox anymore, right? And while many of you can say that I'd rather get 20 oxen or 30 oxen, maybe that is a better solution than getting 10, 24 chickens, we are also forced into that direction. Does anybody know why? Why are we actually moving towards chickens and not more oxen?
Haven't we reached some kind of limit with the single ox in terms that it can't?
Yes, you can't, but we still have oxen, which would be the fastest processor you can buy today, right? But we are still moving towards chickens. So what I'm saying is that it's not there on this slide. I assume that some of you would have argued that I should use 10 oxen instead of using 1,000 chickens anyway. Yes?
It's typically cheaper to
scale horizontally than vertically? Like it's cheaper to throw more machines at something?
It is, but the main reason is actually this. The reason is that, so what I would call as an Oxen would be like a good, beefy Intel processor, something that runs on a server. But the laws of economics takes over. So ARM, which wasn't really that popular a few years ago, has become the dominant, semiconductor producer. So there's a lot of, so Cray, the company that Seymour Cray founded, died out and rose from its ashes later. But the first time it died out was when Intel chips, basically the Pentium chips, became very cheap. They were bad for supercomputing, but they were just so cheap that people would do it. Right now, if you want to buy a sort of a ARM-based SoC, it's like about 80 times cheaper than buying a high-end Intel chip. But the difference in performance is maybe only a factor of 10. So there's always this, the economics. So if I simplify it to a certain extent, say that there's a 10-fold advantage in going for the cheaper chip, right? So it's in cost, it's so much cheaper. You can buy one for a few dollars almost, whereas you're spending $80, $90 for a single. Yes.
Couldn't you argue as well on top of that and arming with it that, we have, we just say throw another processor at it or whatnot, but we don't have the actual languages or techniques in our repertoire to actually use multiple cores simultaneously.
No, absolutely. So this is the case. What would a better answer? So along your own lines, what would be a better answer here? Along the same lines. That's the missing picture you don't see there. Yes?
Wouldn't it be to have some oxes and some chickens and know how to use them wisely? Or
No.
Have neither?
You invent a tractor. So you want to design better algorithms, right? At the end of the day, that's what it is. And I want to tell you this because a lot of people would disagree, but Hadoop goes this way. A lot of analytics just say, let's throw more oxen, let's throw more chickens. You don't have to be operating at that level. You can do better, and the goal is to design a better algorithm. You have to think outside the box. You have to figure out what is the best way to do it, and then we're going to end up with the right solution. And so effectively, when you're thinking about it, and I'll repeat this throughout this class, is that don't sort of jump into this notion that this is a large problem, I need to throw it at 100 processors. You need to start thinking from the perspective of what is the best way to solve it. And in many cases, the solution might be to come up with a tractor. And it might be as obvious as something like this. This is at least 100 or 150-year-old example. But you're not thinking of a tractor here because you're thinking of oxen and you're thinking of chickens, but you're not thinking of coming up with a tractor. And that's what you need to really think about, is that what is the best way to solve the solution and not necessarily plow down a path that everybody else is taking. So always think in terms of the solution in its entirety. Don't take a problem and just throw it at the machine that you have available. Think in terms of the best algorithm for the best architecture that you have available and something that maps onto the problem that we have.